Hey, good afternoon, everybody.
Good afternoon, Professor.
So I think we're still going to have a few people straggling in, but let's get started for tonight. First thing that I have to address, I guess, is found a boo-boo in last Tuesday's presentation, and it's a mistake worthy of noting and correcting. So I fixed it on this presentation. I'll show you where it lies in a second here, and I also fixed it on the presentation I put on Blackboard, which was called Lecture 6, June 16th, BU. The BU stand for backup. So I fixed it on that one too and reloaded that onto Blackboard. So when you get a chance, please download the new version of Lecture 6 and you'll see this change. So the change that I made is right here. Okay, so it has to do with the minimum steel. And somehow when I was putting together the examples, I kind of got this messed up. But the rule is if a T-beam or L-beam has the flange in tension, so you have tension on the top, compression in the bottom, like I'm showing here, basically you have a negative moment. If the flange has tension, then B sub W shall be the lesser of the effective width B sub F and 2 times the web thickness B sub W. And so that is what goes into these minimum checks. So this was correct. This is still the way that I had it. This is correct for T-beams where the top is in tension. But then all of my examples that I did were the opposite, where the top was in compression. So I don't know how I got into putting the wrong one in there, but it followed through every example. So what I did is I went back and fixed these. Let me find, okay, so this was example 2 that we did last time. Check the maximum steel ratio, that was fine. Here, check the minimum steel requirement. Here's your 2 equations for the minimum steel. And I had B sub W was equal to 2 times the actual B sub W. And that was incorrect for a beam that is in positive bending. So this is fixed. B sub W is 20 inches because the stem width is 20 inches. And I fixed all the equations and all the answers from there on out. So I went through and fixed example 2, 3, 4, and 5 for this little boo-boo. And then we had left off just getting started on example 6. So that's what I fixed, and you can also download the latest version that's been fixed from Blackboard. Okay, so any questions about the minimum width or minimum steel and the width that you use for the equation?
Professor, just clarification. So for the lecture 6 revision, the revised document, it's examples 2 through 5 that you make changes.
Yes.
Okay.
Yes. Yep. Exactly.
The professor for the BW, we just don't double it. We just use the BW that we have.
That's right.
Okay, perfect.
Yes. So let me rephrase it, or let me just state it one last time. For a T-beam, if you have positive bending, so the top is in compression, the bottom is in tension, like we've been doing all of our examples, then the B sub W that goes into, let me find those equations. The B sub W that goes into these minimum steel equations right there and right there is the width of the bottom. If you have a T-beam that is in negative bending, so the top is in tension and the bottom is in compression, then that's when you use the 2 times BW or B sub F, whichever is smaller. Okay, does that make sense?
Yes, thank you.
Okay. And let's see, one other thing. I don't see him yet. Okay. All right. Before we pick up where we left off for the conclusion of T-beams, does anybody have any questions or issues they'd like to bring up?
Professor, for the problem 2 that we were discussing, would it be well, would you not recommend using tables for that type of beam, or like would you prefer seeing the moment diagram, or does it matter?
That's a good question. If you can find tables and use the tables correctly, then I have no problem with getting your moments from tables, load tables. But for the one where I've asked you to skip load, so there's a problem in homework number 3 where I've asked that you investigate the beam that has a cantilever on it with skip loading. Skip loading means that live load is unpredictable. It could occur here or there or anywhere. And so you have to design for the worst case. And so in the example where we have a beam with skip loading, I think it would be more instructive to go through and draw a shear and moment diagram for each one of the skip loaded cases that I've listed. And when you do that, see the difference between using a table and drawing a moment diagram is when you draw the moment diagram, you get the whole picture. And I think for that case, that would be more instructive.
Yeah, I was thinking the same thing. Okay.
Okay. Anybody else questions on homework or anything? Okay. So where we left off last time, there it is right there. Example 6. Okay, so example 6 is another design problem where we do not know what the effective depth is, and we don't know what the area of steel required is. What we do know is the shape of the T section is 50 inches wide with a 3-inch flange, and I have 4,000 PSI concrete, 60 KSI steel. The width of the effective flange is 50 inches. And again, as I mentioned before, if you see a problem stated in this way, then there's no need for you to go through and calculate 8 times the flange thickness plus halfway to the next beam or the span over 4, anything like that, because I've already reduced the problem to the section that I want you to evaluate. Okay, so in a real world, you're never going to see an isolated T just like this. But for the sake of the problems, without repeating that first step over and over, sometimes I'll just give you what the effective width should be for the problem. Okay, so for this T-beam, Design steel reinforcement to carry a design moment M sub U of 2,000 kip feet. The depth and width are unknown. Use an iterative procedure. Aim for epsilon sub t equal to 0.0125 and use bar rebar equal to or smaller than number 11 bar. So those are our directions. Keep in mind these designs where you don't have a depth at the beginning of the problem. If you don't have a depth at the beginning of the problem, then you need some kind of target for, what am I supposed to aim for? Or else there's an infinite solutions that are all correct if you don't have something that kind of hems it into what we're looking for. So this one is epsilon sub t 0.125. The next problem could be rho is equal to 0.18 times f prime c or fy. The next one could be epsilon sub t equal to 0.05. So that's for me to tell you in the beginning of the problem statement, kind of to guide the process to what we're looking for. Okay, does that make sense? Okay. So this is our guide. We want epsilon sub t to be equal to 0.125. It's never going to be exactly equal to this, but that's what we're aiming for. And of course, we have to have a strength greater than 2,000 kip feet. So we start with a simple guess for D and assume, and A sub S, and assume B sub W is equal to D over 2. So the width wasn't given either. So I'm going to just use as a ballpark that the width is equal to the depth over 2. So if I make D equal to 36 inches, then the width of the stem is going to be 18 inches. And now I can start with my index. R sub n is mu over phi bd squared. So mu, 12 inches per foot, and phi bd squared gives me 412 psi. From table A13, I can look up that with 412 psi, the rho I need is 0.074. So my steel required is rho BD, 0.074 times 50 times 36 gives me 13.32 inches squared steel. We don't need to choose our bars just yet, as we're still just in the approximation stage. We're just kind of trying to hone in on a solution. We don't even know if this is going to be a rectangular beam or a true T-beam yet. So there's a lot of iteration that goes into this. We are going to assume that it's rectangular. If it was rectangular, then A is equal to ASFY over 0.85 F prime CB. So I plug in my values. I get 4.7 inches. 4.770, there's a typo. 4.76 inches is less than 3 inches. It's actually greater than 3 inches. So therefore, the rectangular assumption is invalid. So I got a typo there. So now I have to consider it as a true T-beam. If it is a true T-beam, then that means all of the flange is going to be activated. So the force in the flange is equal to 0.85 F prime C times H, the thickness of the flange, times B sub F minus B sub W, because I just want the overhanging flanges, so I take out the web. 0.85, 4,000 psi, 3 inches deep. 50 minus the 18 that I assume my width is going to be gives me 326.4 kips. So C sub W, the rest of the compression, is equal to the tension minus the compression in the flange. So I've got 0.85 F prime C BW times A that's my force in the compression in the web, equals T is ASFY, and the force in the flange, I could have plugged this into here, but I just re-inputted this. And so I plug in all the known values, 0.85, 4,000 PSI, 18 inches. A is a variable, 13.32 times 60 KSI, minus 0.85, 4,000, 350 minus 18. And I condense it to 61.2 kits per inch times A, 799.2 minus 326. And I get A is equal to 7.73 inches. So this diagram is what we just did. All the tension equals all the compression. A is unknown, but I know the force in the flange because it's fully activated. I know the force in the web because the force in the flange plus the force in the web equals the tension. So I can solve for little a. Do I have any questions about this part?
For the homework, although it doesn't specify for us to assume it's rectangular, we should take this approach now. We assume it's rectangular for each homework problem, even though it doesn't sort of remind us or tell us?
Yes, yes. The answer is yes. We always assume that we always assume that it's going to act like a rectangular beam, because most of them do. Most of the time it does act like a rectangular beam. And if it does act like a rectangular beam, the whole problem is a lot simpler. So you don't want to get into all this complexity first and then find out, oh, it was rectangular. I could have been done half an hour ago. See what I mean?
Right on. Yeah.
So you always assume the simpler case first until you get to that step we just did where you prove that it's not. Okay, the other question I got was, in the beginning, how did you get D equal to 36 inches? Complete guess. You'll see here in a minute the iterative process here. 36 inches is not the final answer. I just made a complete guess and just threw it out there. All of this, the problem that I'm doing, you'll see that it's a lot of hand calc. And there's absolutely nothing wrong with taking some of the key points of this and programming it into Excel, for example, or I use MathCAD as well. You can use those as design tools and then have your iterative variable, you just put that in a cell, and you can very quickly just change the number and hone in on a solution. And then if you were to do that in Excel, then just transcribe your final answer to your homework problem or to, by hand to finish it out. But you can always kind of automate certain parts of this so you're not doing page after page after page of hand calcs like I'm about to do. So, but I want to make sure everybody's clear about, let's get back here. Okay, so this point here, the force in the flange is solvable. Once we figured out that it's a true T-beam, then that means A is lower than the bottom of the flange. That means I don't know what A is, but it also means that I know the flange is completely stressed to 0.85 F prime C. So without any iteration at all, I know exactly what the force in that flange is. So the red part is totally solvable. I made a guess for the steel, so that's solvable. The tension is ASFY. The only part that's unknown now is the force in the web. I can get the force in the web by summing my forces equal to 0. And once I get what the total force in the web is, I can solve for little a. So that gets me little a is 7.73 inches. So from my table, I find for this strength of concrete, beta 1 is 0.85. So C is 7.73 over 0.85, 9.09 inches. And then I can solve for epsilon sub t. I plug in my D that I'm guessing at with my C, and I get 0.00888 inch per inch. So is there anything wrong with 0.00888 inch per inch? Anybody?
It doesn't meet our requirement.
It doesn't meet our target. Exactly right. It is smaller than what we want. There's nothing wrong with this value code-wise. It's just that the problem was set up with a target, and we have missed our target by quite a bit. So I just want to be clear, why this is not okay has nothing to do with code or strain or cracking or anything like that. It's just not what we were looking for in the beginning of the problem. So therefore, I have to increase D. Actually, I think I have to decrease D. I got that backwards too. No, I made it bigger. Think about that for a minute. Oh, yeah. The strain's not big enough. Okay. Okay. Epsilon sub t is perfectly fine. It's greater than 0.005, but I want more fluff in it. So I got to have a bigger D gives you a bigger epsilon t. So I'm going to try 38. I started with 36. Let's try 38. And so I repeat this process. These are going to be the same, 0.9. The width is the same, but here's my new D, 38 inches squared. Now I've got 369 PSI. So from the table, I get 0.0066 for rho. So then AS required is 0.0066 times 50 times 38, 12.54 inches squared. This is my C sub W is equal to T minus C sub F equation again. And I solve for A is 6.96 inches now. So C is 8.19 inch. So epsilon sub T is now 0.1092. So we're going in the right direction. This is closer than 0.00888 was, but not quite close enough. So I try 40 inches. Starting to see where my comment about plugging this into Excel might be a time saver on these.
Professor, during a test, could we put this into Excel?
During a test, no. I have to write these problems so that you don't have endless iteration.
Okay.
That's on me, because
Okay.
it wouldn't be fair to write something that takes you, I mean, this is just kind of becomes busy work at a point. And during the test, the school is making us use this Respondus lockdown browser. So you're not going to have access to Excel
Okay.
or anything else for that matter. So during the test, the only thing you have access to is a calculator and a piece of paper. So I have to be very cognizant of that when I write the test.
Okay, thank you.
Okay, so we're going to try D equal to 40 inches and repeat. There's my 40 inch squared. Now I'm down to 333 PSI. From the table A13, I have rho is 0.0059. So AS required is 0.0059 times 50 times my new D of 40, 11 inches squared. And so C sub W, T, C sub F, and I put in my 11 inches squared here. Everything else is the same. And I get A is equal to 5.45 inches. C is A over beta 1. 5.45, 6.41 inches. So epsilon sub t is 40 minus 6.41. And I'm at 0.1572. Dang it. So let's try 39 inches. I calculate R sub n, 351 psi. From the table, I get 0.062. AS required is rho times BD. Gives me 12.09 inches squared. This, again, same equation. This is your C sub W. This is your T. This is your C sub F. And A is 6.52. C then is 6.52 over 0.85, 7.67 inches. And so epsilon sub T is 39 minus 7.67. And here we go, 0.1225. Pretty close to 0.125. Close enough. Okay, now we're in the ballpark. We're not even close to being designed yet. We're just kind of in the ballpark. And so whoever asked the question at the very beginning, which was a great question, how did I start with 36? Well, if you had started with 40, you would have gotten closer faster. If you had started with, say, 18 inches and just had no idea, then you would eventually get here. You would get here, but it would take quite a bit more iteration. A is not supposed to be inch squared. Where did I do inch squared? Eric, help me out. Where did I have?
Oh, for the C equals A over B1.
Ow. Yes, right there. You're right. Yep. Okay. What if we overestimate the value D? I started and ended up way exceeding Q. Okay, that's a good question. The question was, what if I overestimated a value D? Like if I started with 60 inches as my guess and ended up way exceeding the given requirements. Well, that's a good question. And what you would have seen is if you had started with 60, then this one is at 40, and I got 0.15 greater than 0.125. So even at 40, I said, that's too high. I'm going to try something smaller. If you had started at 60, then this number would have been like 0.25, way bigger than 0.125. And you would have iterated again. So again, you would have had more iterations before you kind of honed in on that 39 inch that we just honed in on. We did 36, 38, 40, we did 4 iterations. The farther off you were in the very beginning, you just would have needed more iterations. Okay, Garrett asks, what does design for max positive and negative moment mean? You're not doing your homework while I'm talking, are you? Okay, so what that means is maximum positive moment is a moment that tends to crack the beam at the bottom and puts the beam in compression at the top. A negative moment is the opposite. A negative moment puts the top of the beam in tension and the bottom of the beam in compression. And it's very serious. You need to know what the difference is because you need to know if you need to put the steel on the bottom or on the top, if we're positive or negative bending. So when you draw your moment diagrams, if you draw your moment diagram correctly, you will see that some of the beam is under positive bending and the rest of the beam is in negative bending. And you need to pick where is the worst or the largest magnitude of positive bending and where is the largest magnitude of negative bending. And those 2 points, whichever one of the loading schemes creates those 2 points, those 2 points then become your design MU. And they're different. One design MU is for the bottom of the beam in tension. The other design MU is for the top of the beam in tension. Does that help? Okay. All right. So any other questions? Anybody have anything else on your mind?
Professor, I missed that first part. You said the max positive moment cracks at the bottom and the top of the beam is in compression, whereas the max negative moment is opposite of that?
That's correct. Yes.
Okay, I wrote it. Thank you.
Okay. Bear with me a second. Nope, didn't join me. Darn it. Okay. All right. Just in case that Jeff is one of our students, just in case Jeff, you're listening to this as a recording because I don't see you on the list here. When we talked in office hour, I gave you the wrong number. So the live load moment I said was 13 times 10, and then we factored it, but it's actually 13 times 20, and then we factor it. So I just want to make that correction, and hopefully you'll listen to this later. Okay, back to our problem. All right, so now we're in the ballpark. So we're going to be shooting for a design D of 39 inches. And at 39 inches, we found that we need 12.09 inches squared of steel. So we're going to choose some steel. And remember, the problem statement said use number 11s or smaller. So I'm going to start with number 11s. And if I choose 8 number 11s, that gives me 12.48 inches squared. That's pretty close, but still more than my requirement. According to the table A.5, our minimum width B sub W for 4 number 11s, because I'm putting them in 2 rows. So our minimum width for 4 number 11s is 13.71 inches. So we're going to stick with our BW equal to 16 inches. Actually, what did we use before? Row B. Oh, didn't matter. Oh, yeah, because we're using the, okay. So we're going to use 16 inches, which is, let's see, 39 inches. It's kind of in there. It's not exactly half of 39, but you can see there's a lot of engineering judgment that goes into these. But I'm going to choose 16 inches because I can easily fit 4 number 11s in that width. So with 39 inches as a target and 2 rows of number 11 bar, then my minimum height, and I found that this is a little confusing for folks as well. So please chime in if this is bothering you. Design-wise, we're aiming for D equal to 39. So the height of the beam is going to be 39, plus we've got half of the minimum space between the rebars. The minimum space between the rebars is 1 inch. So a half of that would be a ½ inch, plus the diameter of a number 11 bar, plus the diameter of the number 4 bar tie that's underneath the number 11 bar, plus 1½ inch clear. That's the coverage to our steel. And that all equals 42.91 inches. So again, my target D, half of the ACI section 2522 minimum space between layers of 1 inch, diameter of the number 11 bar, diameter in the number 4 tie, minimum coverage, and this was from table 20.6.1.3.1. Okay, so with a minimum height of 42.91 inches, we choose a value that's to the nearest 2 inches. So I'm going to choose 44 inches. Now this is the part that gets a little confusing, is I had to design D. I used that to find H, but the H that I found was 42.91 inches. Where did 44 inches come from? 44 inches comes from, let's put it this way. If I draw a beam on my plans, my structural drawings, and I say I want a beam that's 42.91 inches tall, somebody's going to come into my office holding a shovel and whack me over the head. Nobody has form work to build a beam 42.91 inches, and nobody's going to build a beam 42.91 inches deep. That's not how it's done. Forms are modular, and so they are basically set up in certain modules, and most likely to the nearest 2 or 3 inches is what you can do. Even 44 inches, I might get some flack about that. They might say, we're not doing 44, we'll do 42, which is 3.5 feet, or we'll do 48, which is 4 feet. I'm not sure, but certainly nobody's going to build a beam that's 42.91 inches tall. Okay, so everybody clear how I got the 44? Okay, well, now that I have a chosen depth of concrete, now I need to figure out what D really is. The 39 that we had was my target. Is there a source that lists typical sizes of concrete beams, you mean? Or rebar? Concrete beams. No, no, I haven't seen that. Concrete is still custom made for every job. There are some pre-made forms, but they're proprietary. In other words, you may have a company like McCarthy, and they put a big investment, hundreds of thousands of dollars, into a whole bunch of beam beds, forms that are, say, 18 inches wide, 36 inches deep. So if you do a job with McCarthy, they're going to want you to design your beams to be 18 by 36. But if you do a job with Baumel, and I'm just making this up, but maybe Baumel made a huge investment in beams that are 20 inches wide by 30 inches deep. So it's more of what the contractor has invested in rather than any industry standard when it comes to these depths and widths of beams. Some jobs are actually custom formed. That's very expensive, but they, go out there and they cut up plywood and build the forms to what you want them to build. But there's very little standardization other than don't dare give us stuff that's not on a normal 2 or 3 inch module. It's very different than the steel industry. The steel industry, a long time ago, standardized all the beams. So all the wide flange beams are all rolled from the steel mills. Doesn't matter what company, doesn't even matter what country, they're all rolled to the same standard shapes that you find in your steel manual. There's nothing like that in concrete. So hopefully that answers your question. Okay, so now we're going to calculate what our actual D is going to be. So I have my beam height that I chose as 44, and I just work it backwards. Minus half the space, minus the diameter of a number 11 bar, minus the diameter of the number 4 tie, minus my required coverage. My D is going to be 40.09 inches. And there it is. There's the illustration. So I have 2 rows of number 11 bars. So it was half the space, the diameter of the number 11, diameter of the tie, and the coverage below that. That gets me to 40.09. And then what I'm going to do is solve for A. I'm going to re-solve for A. I could have made this a little clearer. This term here is C sub W. This term here is my tension, T. And this term here is C sub F, the force in the flange. And I made a few changes. I think I had 18 before, now it's 16. And I have my correct area of steel that I'm going to use here. So I have to recalculate A. A turns out to be 7.39 inches. Calculate C. C is A over beta 1, which is 7.39 inches squared over 0.85. So C is 8.69 inches. Epsilon T, 0.003 D minus C over C. And I plug in, see now this is different. I plug in my real D, not my target D, and my values for C, and I get 0.1084. Now, right here, you might have noticed, wait a minute, professor, that's not 0.125. You're right, it's not. There's a lot of iteration that goes into these design problems. And at this point, after all of this, I've basically am saying now that was a target. That got us to this step, to this step, to this step, and this as a final answer is okay. And it's most certainly larger than 0.005, so we're nowhere near our maximum steel ratio. Okay, so therefore phi is equal to 0.9. Now I have to do my final design check. I never walk away from a problem without proving that phi mn is greater than mu. So we're going to do our check, and I'm summing all my forces from the top of the beam. So the tension force, ASFY, times D, minus the force in the flange times H over 2, minus the force in the web times A over 2. And I resolve for my force in the flange, 346.8. Force in the web, here's my little a, 402. And I already had T is up here somewhere. And so Mn, the nominal capacity, is 748 times 40.09 minus 346 times 3 over 2 minus 402 times 7.39 over 2 gives you 28,013 kip inch or 2,334 kip feet. I put a phi factor 0.9 on it. I get 2101 kip feet, which is greater than 2,000 kip feet. And so we have a satisfactory design. Okay, I do recognize these are getting fairly complicated. So by all means, please ask questions as they come up. So does anybody have any questions?
Sir, could you repeat why was 0.01, why was our delta T? Yeah, okay, yeah.
Well, because when you have an initial target, but you have so many unknowns. We didn't know the width, we didn't know the depth, we didn't know how much steel we needed. So we needed a target. Now, I suppose this being significantly less than 0.125, that I could have gone, well, okay, we need to go a little bit deeper. So actually that wouldn't, because look at D actually ended up being about 40 inches.
Right.
So what you'd have to do is, if this was not okay, and again, this has nothing to do with code, this just has to do with your target. Okay. So if this is not close enough, then you'd have to go all the way back to where we iterated 36, 38, 40, 39, we would have to try 40 again and then run the problem all the way down to this point at 40 to see what we get. And I said, oh, okay, that doesn't work. Okay, let's try 42, which would make the total depth 46, and then run it down to this point again. You see what I'm saying? There's like a layer upon layer of iteration. But what I'm saying is that was our target to get these numbers. Once we get these numbers, I'm perfectly fine with this being our end strain in the steel.
Okay, got it.
Okay, and I know that this does make it difficult. This is not the easiest class in the world. In fact, I think steel design is a bit easier because you have standard shapes to choose from. Oh, somebody, okay. I just explained that. Did you hear the re-explanation or to the person who? No, I didn't. Okay. Well, what happened to the 0125, I'll give you the short version. The 0125 got us to 44-inch total height, 16-inch width, 8 number 11s. We kind of honed in on this solution. And that's what the 0125 was for, was to help us get to this section. So once I got to this section, 50, 3, 44, 16, 8 number 11s, and then I run through and I calculate what epsilon sub t really is, I'm saying this is close enough at this point. Back when we were iterating between 36, 38, 40, 39, it wasn't close enough because we're trying to hone in on a solution. But now that we have our solution, I'm saying this is close enough. If this was not close enough, or if we're not happy with this, then what would we have to do? We have to go back and iterate 44 now. We'd have to make that like 46 or 48 and run through it again until we're happy with this. But for this problem, I'm happy with this. It's by far large enough to satisfy the code requirement of 005. So it was really just a matter of, am I happy with my final solution? And I think I am. This does make sense. And here's the real proof of the pudding, is that phi mn is greater than mu. That's what needs to be, that's required by code. You can never violate this, but the target is just a target. Does that make sense? Okie doke. Okay, do we have any more questions on T-beams? Okay, why don't we then, why don't we take a break now? Because from here, we're gonna go into doubly reinforced or beams with compression steel. And it's a whole nother topic. So this is a good place to break. Why don't we, goes back basically 5:50. Why don't we come back at 6 o'clock and we will continue with the next presentation.
All right, perfect. Thank you.
Okay, is everybody back and awake?
Yes.
Excellent. All right, so we're going to start tonight's topic. This is about compression steel analysis and design, otherwise known as doubly reinforced beams. And also just to do a checkup here, get to my table of contents. Okay, so we're in chapter 5 now from your reading, so in your textbook. So we've already covered 1, 2, 3, and 4. We're in chapter 5, and we have already gone through sections 5.1 through 5.6, and now we're starting section 5.7 for compression steel for tonight. Make sure that we're keeping up on our reading. And then the next lecture after this one is going to be shear design, is chapter 8. And then we're going to get to serviceability issues, which is chapter 6. And also, I was just looking at our syllabus, and our midterm is 2 weeks from tonight. Keep that in perspective. Okay. So what is a doubly reinforced beam? What does that mean? Well, it means that for a beam that has positive moment on it, like this is showing, where you have tension in the bottom, compression in the top, what it means is, in addition to the steel at the bottom of the beam required for tension, we're also putting some steel in the top of the beam. And the steel in the top of the beam is located so that it picks up some of the compression that otherwise would be resisted by concrete alone. This is not the same thing as a beam resisting negative moments, where the tension is in the top of the beam. So that's not what we're doing. We're doing a positive moment beam, tension's in the bottom, but we're putting some steel in the top to pick up some of the compression. So compression steel is steel placed in the compression zone of beams. Compression steel. It is for simply supported beams with a positive moment, there is steel located at the top of the beam. Beams with compression steel are also known as doubly reinforced beams. And the purpose of the compression steel is deflection control, moment reversals, facilitates tie-in to rebar cage, increases the flexural capacity, but not directly. We'll get back to this. Compression steel picks up some of the compressive force, thus the concrete resists less force. So the concrete's picking up most of the compression. Without any steel up here, it's picking up all of the compression. You put some steel up in here, it picks up, the steel picks up some of it, the concrete's still picking up most of the compression. If the concrete resists less force, then the compression block is reduced. And this is little a is reduced. Since C is equal to A over beta 1, when we reduce A, we're reducing C. Since epsilon sub t is 0.003 d minus C over C, when C is reduced, epsilon sub t increases. Thus, what compression steel does for us, compression steel adds very little direct strength, but it allows for more tension steel to be added when the maximum allowable tension steel is inadequate for the applied moment. More tension steel does directly add to the strength of the beam. Okay, so compression steel in terms of strength really doesn't help very much at all. You can put a lot of steel up there and it just increases the strength of the beam by a few percent, like 5%, 6%. It doesn't add much strength at all, because what does it do? The compression steel makes the concrete take less compression. If you have less compression in the concrete, then the dimension A gets a little smaller, and your moment capacity is tension times D minus A. So it doesn't add tension at all. All it does is increases the lever arm by just a little bit. So directly, it doesn't add much at all. And if you have a beam that's not really stressed to its maximum, then compression steel doesn't really help with strength at all. But if you have a beam where you put in all the steel you can put in there, epsilon sub t is 0.005 or less, and you still need more strength, then whatever steel you put up here, you can add that much more steel down here, and that is how you get more strength. Okay, does that make sense? Or do we have any questions on that principle?
It makes sense.
Okay, thank you. Whenever we're talking about compression steel, we denote it with an apostrophe. So the area of steel is A sub S. A sub S prime is compression steel. D is the distance to the steel. D prime is for compression steel. Rho prime is compression steel, etc. So here's a side view of the mechanics. And here's my beam. And now I got steel top and bottom. Apply a moment to it. This is my strain diagram. My strain in the concrete is still maxed out at 0.03. That's my maximum concrete strain. And based on the proportions of steel to concrete, we have our distance C, which then determines our strain in the steel at the bottom, like we've been doing. But now we have a new component up here. Epsilon prime S is the strain in the compression steel. And this is going to become the trick of designing for compression steel. Epsilon prime S will always be less than 0.03. If you look at the triangle, it can never be more than 0.03. And rebar yields at 0.0207. So the question is always going to be, did that compression steel yield or did it not yield? That's going to be our trick. Here's little a, and I'm summing my forces. I have T in my tension steel. I have C sub S for the compression in the compression steel, and C located at A over 2 for compression in the concrete. Any questions on what you're seeing?
Professor, so when you say that's going to be a little trick, what do you mean? So now we're solving for for delta of S prime being less than 0.03.
Yes.
Okay.
For T-beams had two distinct behaviors. Either a T-beam thinks it's a rectangular beam, or the T-beam behaves like a true T-beam. So we assumed one, and then we ran it down to a point, and then we either proved that it was, or we proved that it wasn't a rectangular beam. And whatever the answer was to that dictated how we finished the rest of the problem. Compression steel beams are the same way. We're going to assume that the compression steel is going to yield. We're going to bring the problem down to a certain point, and then we're either going to prove that it does yield or it doesn't yield. And that will dictate how we finish the problem.
Okay.
And it's pretty much what I just said. The trick with compression steel, looking at the strain diagram, the strain in the compression steel is always less than 0.03. So depending on the proportions of tension steel to compression steel and the distances of D and D prime, sometimes compression steel will yield and other times it doesn't. For analysis and design, similar to T-beams, we must first have to make an assumption and then verify that assumption was either valid or invalid. For doubly reinforced beams, we first assume that the compression steel has yielded. If proven wrong, then we start over and solve for the actual strain in the compression steel. We can use the following test. If rho equals AS over BWD, and that's a typo. That's a pretty important one too. That's supposed to say rho prime. And rho prime equals AS prime over BWD, then, and this is important too. Unfortunately, I biffed, that's supposed to be rho prime right there. But this D is not D prime. So when we evaluate rho and rho prime, it is the AS or AS prime over BWD. Both of them are BWD. Okay, so this is not a typo. That's not supposed to be D prime. Okay, yeah, so with my typos, everybody clear? Rho prime is equal to AS prime over BWD.
Yep.
Okay, so here's our test. If rho minus rho prime is greater or equal to 0.85 beta 1 F prime C over Fy D prime over D 87 KSI over 87 KSI minus Fy. If this is true, then the compression steel will yield. And this equation here is valid for 60 KSI and 80 KSI rebar. So epsilon Y 60 over 29,000 is 0.00207. And this is how this ratio comes to 0.003 divided by 0.00207, the yielding strain, times 60 KSI is 87 KSI. Or the yielding strain for 80 KSI is 80 over 29,000 is 0.00276. And 003 divided by 00276 times 80 KSI is still 87. So this is just a quick proof that this equation is valid for both 60 and 80 KSI. If it fails this test, and rho minus rho prime is less than this term, then the stress in the compression steel must be solved for. Remembering our bilinear assumption for the stress in the rebar, if compression steel has not yielded, we must find the strain epsilon prime S by similar triangles and use Hooke's law to find the stress. So here's steel. Once you hit your, that's kind of small to see, but that's the yielding strain. Once you hit the yielding strain, we assume that the rebar is just straining forever at 60 KSI. But if you're somewhere between 0 and the yield strain, then it's a linear elastic relationship. And so if you have the strain, you can solve for the stress in this elastic range. Any questions on that? Okay. So using Hooke's law, F sub S prime, the stress in the compression steel, is epsilon S prime times the Young's modulus E sub S, where E sub S is 29,000 KSI for all grades of rebar. The following expression can also be used to find F prime S, where F prime S is equal to 87 KSI C minus D prime over C using similar triangles. Okay, so back to our diagram here. Once F prime S is found, then we can find our force. C sub s is equal to A prime s times F prime s. T, the tension force at the bottom, is always ASFY. And by summing the forces, the concrete compression is found. Again, if you look at this diagram here, summing our forces in the x direction, T has to equal C plus CS. So rearranging this, I have C is equal to T minus C sub S. So by mechanics, my compressive force is 0.85 F prime C B times A. Therefore, A, little a, is equal to T minus C sub S over 0.85 F prime C B. Okay, so are we ready for an example?
Yeah.
Yes, please.
All right, so here's our beam. This is an analysis problem because everything has been pre-selected for you. You have 6 number 8s at the bottom at 20, D is equal to 22 inches. You have 2 number 8s at the top, D prime is 2.5 inches, and B sub W is 10 inches wide. The concrete is 3,000 PSI, the steel is 60 KSI, and what we want to find is our capacity Φmin. Solution. Let's find the area of steel. 6 number 8s at the bottom, 6 times 0.79 inches squared, gives me 4.74 inches squared. D is 22 inches. Missed the prime again. A prime S is 2 times 0.79 inches squared, or 1.58 inches squared at the top. And D prime is 2.5 inches. B is 10 inches. So rho is 4.74 over 10 times 22. That gives me 0.2155. I'm getting really frustrated. I missed all these primes. Rho prime is equal to 1.58 inches squared over 10 over 22. Again, this is not D prime, this is D, and that is 0.0718. F prime C is 3,000 PSI, therefore beta 1 is 0.85. So we do our test. If rho minus rho prime is greater than this term, then the compression steel will yield. So we do our test, we plug in rho, we plug in rho prime, and I get 0.1436. And in this expression, I plug in my values. Beta 1 is 0.85, F prime C is 3, Fy is 60, D prime over D, 87 over 87 minus 60. And I get 0.1323. So rho minus rho prime is greater than this term. Therefore, the compression steel is going to yield. So that makes this pretty easy. If the compression steel yields, then I know what the stress is in the compression steel. It's going to be Fy. So C sub S, the force in the compression steel, is equal to A prime S times Fy. 1.58 times 60 KSI is 94.8 kips. The tension force is ASFY. 4.74 times 60 is 284.4 kips. So little a is equal to the compression in the concrete over 0.85 F prime CB. The compression in the concrete is the tension minus the compression steel, which gives us 284.4 minus 94.8 over 0.85, 3 KSI, 10 inches wide, and I get 7.44 inches. Therefore, C, this is big C, is 0.85 F prime C B A. I plug in A, I get 189.7 kips. So here's a summary of my three forces. And you see how the compression steel just took a proportion of what would have gone to the concrete. If we had no compression steel, then all this 94.8 kips would have been carried by the concrete. To find the capacity now, we're going to sum our moments about the top of the beam. So I have the nominal capacity is tension times D minus the compression in the concrete times A over 2 minus the compression in the steel times D prime. And I plug in my values and I get Mn equal to 5314 kip inches or 442.8 kip feet. C is A over beta 1, 7.44 over 0.85, and somehow I got this inch squared on every one of these. Stuff like that would just drive you crazy. So C is 8.75 inches. Epsilon sub T is 22 minus 8.75 over 8.75. And I get 0.00454. That is less than 0.005. Since epsilon sub T is less than 0.005, then according to table 2122, phi is 0.65 plus 0.25 epsilon T minus epsilon Ty, that's the yielding strain, over 0.005 minus epsilon Ty. My yielding strain is Fy over E. 60 over 29,000 is 0.00207. And so I plug this back into here, and I get a phi equal to 0.861. So phi Mn is 0.861 times 442.8 is 381.3 kip feet. And we can check, did the compression steel really yield? Using similar triangles, I can go back and back calculate what the strain in that compression steel was. It was 0.0214, which is greater than 0.0207, and so it did in fact yield. Okay, I have a question. Let's see, how does W, which is right at the top, crack? Okay, no. Is it okay if I read your question so everybody knows what I'm talking about? Okay, so I have a question that says, how does doubly reinforced concrete, which has rebar on top and bottom, crack? In all these calculations, I don't know. How do you know which side is tension steel and which side is compression steel? Does the fact that there's more steel on the bottom and less on the top, is that where the concrete cracks? It will still crack at the top. And no, but I'm glad you asked. I very much want to clear up that misconception. Because I'm sure it's a common one. Okay, so let's do it this way. If I do my little stick figures and I draw a little simply supported beam, and I don't like that one. There we go. Okay. Here's my situation. Now, is it clear that if this is my situation and this is my load, that if this beam is going to crack, it's going to crack right there first? Okay, so the technical term, why did it crack here at the bottom first, is because when you have a simply supported beam, and you apply a load that's coming down on it, like I show here, that produces a positive moment. So the simple answer to your question, the beam is going to crack on the bottom because it is in positive bending. And positive bending does not care where you put the steel. I could have steel here and I could have steel here, doesn't matter. Positive bending, a smiling face. Yes, it is, but that's the deflected shape. Okay, let me finish this, and then I'll getting too many overlaying questions. This is positive bending. So simply supported with the load coming down produces positive bending. Positive bending by definition always produces tension on the bottom, compression on the top. And it doesn't matter where you put your steel. You still get tension on the bottom, compression on the top from positive bending. And you can see that a massive mistake would be to only put steel on the top of a beam that has positive bending, because this thing will just collapse. There's no strength at all. Okay? Now the opposite happens if I have a beam and I have a support system that looks like this and maybe looks like this. Okay, now what is going on with this beam? This beam has a moment diagram that looks like this. Okay, so here is positive bending. Here is negative bending. So back to our definitions. Positive bending is going to cause a crack at the bottom. Negative bending is going to cause a crack at the top. The bottom or the top are in tension only due to the moment diagram. That is the only thing that tells you if you have tension in the top or in the bottom. Okay, so that answers where is it going to crack. Where it's going to crack has nothing to do with where the steel is. But where you put the steel better have something to do with where the crack is. But the crack doesn't locate the steel. The steel must be located to find the crack. All right, so the moment diagram dictates where the tension is. Now, let's get back to, okay, so now hopefully I'm getting the question. Let's go back to a beam. Here's a beam. And I've got some steel up here. And I've got steel down. This is horrible, but there's steel there. Okay. Now, how do you know where the cracking is going to be and which steel is in compression and which steel is in tension? You don't. That's the simple answer. You don't. Just because there's a lot of steel down here and a little steel up here would lend you to think that this is the compression steel and this is your tension steel, but you don't know that for sure. You don't know that. So what you have to have a moment diagram, or you have to have something in the problem telling you this is positive bending or this is negative bending. Now, having just said that, many of my problems, I don't tell you explicitly this is positive bending or this is negative bending. So if I don't say that, just assume that it's positive. That's by far the most common case, is that it's positive bending. So the tension's in the bottom and the compression's in the top. But again, like the homework that you guys are going to be working on this week, you're going to have some cantilevers, and the cantilever is going to produce some negative bending. So I'm glad you asked that question. Was there anything else about your question that I didn't cover? Did I hit all the points? Okay. Very good. All right. Any other questions at this point?
That was a good illustration. It's makes more sense now with negative and positive moment.
Okay, great.
Yeah, that was good.
Okay, great. Thank you. All right, let's, and by all means, please, if there's something that you feel like you're lost and I don't know, maybe you feel like you're the only one who's lost, I assure you you're not, but please ask questions. And this class is, how do I say this? Concrete is not the simplest material to learn in the first place. I've taught this many times. It's not the easiest thing. And I can't even be in front of you in the classroom and really kind of get the feel of where everybody is. That makes it even more hard. And then we're doing this over summer where we got a 15-week course squeezed into 10 weeks. So this is challenging. And I get that. And I get that if you haven't worked with this, some of it can be very confusing. So I beg of you, if there's something that I'm losing you on, or I'm just going too fast, I tend to do that too. Please slow me down, ask questions, and you know, we have plenty of time to do this. What would you say the ranking of difficulty is amongst the various materials? Um, Good question. I would say that with the exception of one common material, this is probably the most complicated. And that the one material that is more complicated than this is pre-stressed concrete, which makes sense, doesn't it? Steel was not this hard. I'm sorry. Which is, yes, that is what I do, pre-stressed concrete. Yes, correct. So, but the pre-stressed class, if you ever get a chance to take a pre-stressed class, is it's very interesting because in order to understand the principles of pre-stressing, you really got to get all this stuff that we're doing here down pat. I mean, this is all foundational to the pre-stress class. So it's good. And for those, yeah, steel was not this hard. I absolutely believe you that steel is more standardized. Okay. Any other questions for me? Okie doke. Let's go to example number 2. Example number 2 is very similar to example number 1, except that now we have 3 number 7s up here. And I think I made D a little smaller. Oh, and D prime is smaller. So a few little nuances that we've changed. We now have 5,000 PSI concrete, 60 KSI steel, and we want to find our capacity FMN. Solution. The steel still 6 times 0.79 inches squared is 4.74 inches. D is 19. A prime S is 3 times 0.6 or 1.8 inches squared. D prime is 2 inches. And B is 10 inches wide. So we calculate our rho. Rho is 4.74 over 10 times 19, 0.02495. We calculate our rho prime, again, I'm missing these primes, is 1.8 over 10 times 19, 00947. F prime C is 5,000 PSI concrete, so therefore beta 1 is 0.8. You can find that in your table in the back. So we do our test. 0.02495 minus 0.00947 is equal to 0.1548. But our test, 0.85, I put in beta 1, 5,000 PSI concrete, 60 KSI, D is 2, D prime is 2, D is 19, 87 over 87 minus 60, and I get 0.1922. 0.1436 is less than, where did that number come from? Another typo. Okay, but anyway, both of those numbers are wrong. 0.1548 is less than 0.1922. Therefore, the compression steel will not yield. Okay. It'd be good if you guys have like your downloaded version so you can make these corrections, but this is wrong. But the outcome that this is less than this is correct. And please put a prime and a prime right there. Okay. Okay, so if the compression steel will not yield, then we need to come up with what the stress is in the compression steel. So we need a value of C to use for this equation here. So what we're going to do is we're going to write our force equations in terms of little c. So let me stop for a moment, and I don't remember if I drew a side view. If I draw a side view of this beam, I have tension, I have compression in the steel, and I have compression in the concrete. T, compression in the steel, and compression in the concrete. And what I'm going to do is I'm going to write all three of those forces in terms of little c, all three of them. So the compression force in the compression steel is A prime S times F prime S, but F prime S is equal to this equation here, 87 KSI with C minus D prime over C. So I can put this in for F prime S. So I got 1.58 inches squared of steel times 87 C minus D prime over C. I can plug in D prime, and now C sub S is a function of little c. T is ASFY, so we know that right out. 4.74 times 60 is 284.4 kips. And big C, the compression in the concrete, 0.85 F prime C B A, but we have a relationship between A and C, don't we? A is equal to beta 1 times C. So now I can plug in all my knowns, 0.85, 5 KSI, 10, and 0.8 times little c. And now all three components of the force are defined by functions of little c. I'm going to simplify this to be 34 kips per inch times c. Okay, so T minus C is equal to 0. So I've got 284.4 kips minus this expression for C sub S minus this expression for C equals 0. And using a little algebra, I just condense this into a nice quadratic equation. And then I can solve it. And how you solve it, any way you want. You can use your calculator with a polynomial solver. You can use your calculator and use the matrix method. You can use the, gosh, I don't even remember, b squared plus or minus square root something something over something. whatever you want to do. Just be able to get to this answer. And when I say that, be able to get to this answer without a computer screen. Because you just might find yourself in a situation where you need to be able to solve this quadratic with pencil and paper and a calculator. Now that we have little c, we can solve for a. Beta 1 times c, 0.8 times 5.45 is 4.36 inches. And so I can find f prime s. I plug in c into here, and I get that the stress in the compression steel is 55.1 KSI, confirming that it didn't yield. Yield is 60 KSI. So C sub S is A prime S times F, not Fy. That's a typo. 1.8 times 55.1 is 99.2 kips. T, as we found, is 284.4 kips. And C is 0.85 F prime C B A. So I take my A here, plug it into here, and I get 185.3 kips. Now to find my capacity, I just sum my moments about the top of the beam like we did in the previous example. So tension times D minus C over A over 2 minus C sub S times D prime. And we get 284.4 times 19 minus 185.3 times A over 2 minus 99.2 times D prime. And I get 4,801 kip inches, or 400.1 kip feet. And again, this is my nominal capacity. So I have to solve for epsilon sub t. Epsilon sub t is 0.0746, greater than 0.005, so phi is 0.9. So my moment capacity, my allowable capacity, is 0.9 times 400.1, which is 360.1 kip feet. So in this example, if I had ignored the compression steel, VMN would have been 332 kip feet, or only 7.8% less. So putting those three number sevens up there, which is money, steel is money, only bought me 8% more capacity. Compression steel is only really helpful when epsilon sub t would have been less than 0.005 otherwise. Okay, any questions on example 2?
Professor, so we use the compression steel when we cannot extend our D, right? If we extend our D, we will get more epsilon sub T. So if we have like a space limit, then that's when we use the compression steel.
Absolutely right. Yes.
Oh, okay, perfect.
Yep. You hit the nail on the head. Yeah. The cheaper way to do it is just make the beam deeper. And then you can put more steel in it and you don't have to worry about epsilon sub t. But if you have a headroom clearance, or for whatever reason the beam cannot be deeper, then compression steel is your last resort to make that beam work with a section that otherwise would not work. Yep. Okay. So let's start talking about compression steel design, which is weird because typically one does not set out to design a doubly reinforced beam. It's not very efficient. It's not very economical. So compression steel becomes a last option if the depth limitations do not allow for a viable option to resist the required moment. Just exactly what you just said. If the maximum steel for a given section has been tried, epsilon sub t 0.005, and the member is still not strong enough, then the only last option is to add compression steel so that more tension steel may be added while not further lowering epsilon sub t. In the next example, I will showcase a beam that does not meet the demands of the job and how we can design compression steel to achieve an adequate design. Okay, so example number 3. Here's a beam. D is 22, the width is 20. We got 3,000 PSI concrete and Fy is 60 KSI. So we want to design the beam to carry 650 kip feet a moment, and the beam dimensions cannot be changed. We're stuck with this beam. Solution. So we start off as we do. R sub n is equal to mu over phi bd squared, which is 650 kip feet times 12 inches per foot over 0.9, 20 wide by 22 deep. Gives us 895 KSI, or 895 PSI, I mean. So using table A12 for 3,000 PSI concrete, 60 KSI steel, the maximum value for R sub n is equal to 685 PSI, if you look at that table. Ah, what does that mean? That means that looking at, well, according to this table, we can't carry that moment. We can't get to 895 because the table maxes out at 685. Using table A.7, rho equals 0.136 when epsilon sub t is 0.05, and then AS required would be that maximum rho times 20 times 22, 5.98 inches squared. So if I choose 6 number 9s, then I have an area of 6 times 1, or 6 inches squared. So I find little a, 6 times 60 over 0.85, 3 KSI times 20 is 7.06 inches. With F prime C equal to 3,000 PSI, beta 1 is equal to 0.85. C then is equal to A over beta 1. 7.06 inches squared over 0.85 is 8.3 inches. Epsilon sub t then becomes 22 minus 8.3 over 8.3 is 0.0495. So we calculate phi is 0.896. We just ran this on the last example. You put in the yield strain, and your epsilon sub t. Check assume steel for capacity. Then again, we're starting as a singly reinforced rectangular beam. So I plug in my phi, my area steel, 60 KSI, D, area steel, 60 KSI, 3 KSI for concrete, 20, and I get 5958, or 496 kip feet. That is a far cry from 650. So we're not even close with our maximum steel. Okay, so what I'm doing is I'm starting the problem with a demand that seemingly cannot be carried by this beam, because I put the maximum steel I can put in there. My epsilon sub t is already below 0.005, and I'm not even close. I'm at 500 and I need 650. So what do I do? Well, this is where I would need to look at another option, because epsilon sub t is already below 0.005. So just adding more tension steel is not an option. That would just make this even lower. So I have to add compression steel. Like we did for T-beams, we break the problem into 2 parts, MNN1 and MNN2 for the portion resisted by the tension steel and the portion resisted by more tension steel balanced by compression steel. Again, this is a trick that we do for designing a compression beam when we don't have the proportions worked out. So the trick is sum of the total steel is going to be balanced by the concrete, and that moment arm is D minus A over 2. The rest of the steel is going to be, excuse me, it's going to be balanced by the compression steel, and that moment arm is D minus D prime. So AS1 plus AS2 is equal to the total steel, total tension steel. AS2 is equal to A prime S. These two are balancing the compression steel. And so then MN1 is equal to AS1 times D minus A over 2. And MN2 is equal to AS2 times D minus D prime. So we're splitting the capacity into two beams. One beam is singly reinforced. You got tension steel and concrete. And the other one, there is no concrete. It's just tension steel balanced perfectly by compression steel. Okay. Do I have any questions to this point?
So, Professor, however much compression steel we add, the same amount has to be going into the tension steel on the bottom.
Very close. Let's phrase it like this. Whatever steel, compression steel that you add at the top, you may add that much more steel to the bottom, and it doesn't change epsilon sub T.
Okay.
They balance each other, and it doesn't change. See, like A remains constant if AS1 remains constant. So if you add some steel up here, then you can add some steel down here, and these two balance each other without changing this.
Okay, it makes sense now. Thank you.
Okay. All right, well, I'm looking at the clock and I'm seeing that we're getting kind of close here. I know we have a few more minutes, but I actually probably should have stopped this. I'm seeing example 3 is going to take us beyond our time. So I'm proposing that maybe we pick up next time from where we left off here, and we'll finish out compression steel next time. But we do still have a few minutes, so I'll be more than happy to entertain any questions that you might have at this time.
Professor, till the place we stopped, is this enough for us to be able to finish the homework?
I believe so. I haven't assigned any homework that has compression steel yet.
Okay, perfect. Thank you.
Pretty sure. Homework 3, I don't think has. I mean, that's a valid question. Let me check real quick. Let me find it real quick. Okay. Why did it kick me off? That's weird. I may or may not be able to answer this question. I got kicked out of my drives. Yep, connected. That's weird. All right, so
I don't think we have any doubly reinforced problems for this homework.
that's what I thought.
Which then eliminates lecture 7. So I think we could get away with up to lecture 6 for homework 3.
Yeah, I don't think we even started T-beams yet. I think that's the next homework. Okay, well, I am going to trust somebody else has their homework. I can't get to it for some reason. But I'm fairly certain that homework 3 is just singly reinforced rectangular beams that are either in positive bending or negative bending, but they're still singly reinforced rectangular beams. I think homework 4 then is going to start in with T-beams and compression steel. And then I'm pretty sure that's where our exam is going to take us to. The exam is going to take us up through, I'll decide if it goes to compression steel or not, but certainly to T-beams. Okay, Ashley, I think we just answered Ashley's question. You do not need this example to do the homework 3. Question 2, homework 3, you want us to find all the moment diagrams for all the skip loads and pick the largest positive and negative moments to design with. Yes, that is exactly right. But I'll give you this. On homework 3, question 2, you do not need to evaluate the 3 different loading conditions. You do not need to evaluate them with the 1.4 dead load case. You can look at them with just 1.2 dead, 1.6 live, because that clearly is going to be the one that controls. And no, you're going to design 2 sections. You're going to have one section that's in positive bending with number 9s at the bottom of the beam. And you're going to have another section, same beam, but another section that has tension on the top of the beam, and you're going to use number 10s.
So does that mean the steel will go on the top for the negative moment? I mean,
Yes.
sorry, negative. Yes. Okay.
Yes. Yep. When it comes to differing the positive and negative moments and adding them, how does that work? Well, yeah, we talked about this before, but you can, I think I'm losing my voice. The way that I do it is you take your load factors and you factor your linear loads. So your dead load has so many kips per foot, you factor that by 1.2. Your live load, whether the live load is over the whole span or just the cantilever or just the backspan, you multiply wherever that live load is by 1.6. Now that you have a factored dead load over the whole span and you have a factored live load over the whole span or just the cantilever or just the backspan, for each one of those cases, you now solve for your reactions and draw your moment diagrams. When you draw your moment diagram, you will then see that some of that beam is under positive moment and some of that beam is in negative moment. Okay, that's a good question. No, you are not taking the largest between the positive and the negative. What you're doing is you're taking the largest positive moment anywhere on that span from the 3 different load cases that you're evaluating. And wherever on that span you have the largest positive moment, you're designing the beam with steel at the bottom for that moment. Then you're looking at all 3 moment diagrams that you've created, and whichever one of them has the largest negative moment, wherever that negative moment may be, you're then designing the beam with steel on the top of the beam for that largest negative moment. Okay. Try to remember that problem. Hang on a second. Let me look at this. There might be one other little nuance to this problem. Guys, bear with me just a second. Let me look this up. Design the beam. Oh, yeah. Okay. All right. I'm glad you guys asked this. That beam that has the positive moments and the negative moments, I didn't tell you how deep the beam is. That's part of what you have to design. So here's a trick. Whichever is greater, the positive moment or the negative moment in absolute values, whichever one is more kip feet, that moment is going to dictate how deep the beam becomes. And then the other moment is going to be smaller. You're not going to make that beam shallower. You're just going to use less steel. So do the larger one first, find how deep the beam has to be, and then use that depth to design the other one. Does that make sense? Okay. All righty. If there are any other questions for me? Okay, doke. Then I wish everybody a good weekend. If you have any questions that pop up, you can email me. I'll try to get them when I can. I'll check my emails periodically. And that's it for today. I will stop the recording and we will see you on Tuesday. Thank you very much.
Have a
Thank
great
you,
weekend.
Professor. Have a great weekend.
You too. Thank you, guys.